So I think let the participants join the session and we can wait for 2 to 3 more minutes and then start the session. Okay, so without any further delay, we can start the session. And since there are no doubts, I can go forward and start with the numericals on op-amp based instrumentation amplifiers. So we'll directly jump into the numericals, and the first numerical is on your screen for the viewers to solve this problem. So all the basic concepts we have already covered in the past 2 weeks regarding the op-amps and the Smith trigger circuits. And based on those problems, we will now use cascaded or multiple such op-amp based circuits which are back-to-back connected in order to actually estimate some voltage values in the differential mode. If you provide some inputs, so you want to estimate the output of such cascaded configuration, then you can use this analysis. Now this circuit is given where we have two stages comprising of this differential stage and stage 1 and the stage 2, which are cascaded to each other. Now you are being asked to find, there are 4 parts. So we have been given that the V differential is 2 millivolts, so the differential voltage across the points A and B are given to be 2 millivolt, and then the value of VCF is being asked. So VCF is the potential difference between these two nodes. So this is part 1, and as part 2 we are being asked to find the value of V naught, and as part 3 we are being asked to find the total gain of the instrumentation amplifier, that is for stage 1 plus stage 2. And if all the op-amps are ideal, assumed to be ideal, then the input impedance of this amplifier is being asked. So 4 problems are there within one problem, and you have to analyze this overall circuit configuration to determine these 4 parts. So I request all those who are watching this tutorial to kindly try themselves, first try to solve by your own, and then we can discuss and then go ahead with the solution. So I first request everyone to try this problem. I will give you some time, and the 4 subparts of this problem are seen here on the screen, and I request all of you to try this problem once. So I hope some of you might have solved the problem or might be trying. So enough time was provided. However, since there are no participants, I cannot discuss or interact, but I want to always hear from you. So I guess I will just go ahead with the solution. So just let me take a picture of this circuit and then we can go ahead with the part 1. So what is being asked is to find VCF. Now, one thing to note is that since this configuration, the first stage has a negative feedback, therefore, even if you assume that there is no virtual short being satisfied, then also the output voltage will be such that even if due to the history it went to the VSAT or minus VSAT or the plus VCC, whatever you say, or minus VCC, it will be pulled down to be equalized with the input voltage, which is nothing but the virtual short condition. Why is this happening? This is happening, this reaction or this feedback loop is working to bring down the output voltage and equalize it with the input, only because of the negative feedback. Because whenever this increases, you can assume like this, that whenever this value increases, then the output voltage is also increasing, and since the output voltage is increasing, this voltage is also increasing, and ultimately the steady state will happen where both voltages will be made equal, and hence virtual short will be always satisfied in such configurations. So you can assume virtual short, and I can write holds true, right, for negative feedback circuit in stage 1. So that much we understood, right? So you now have one information that the virtual short will work. So now try and solve the remaining part of the problem to find the first stage, that is VCF, which is being asked. So going ahead, with virtual short condition, what we get is this potential is set to 0, and hence we can assume this as plus VA and this as minus VB, and of course the V difference is already furnished in the problem as 2 millivolts. Now what I can comment is that if this voltage is VD, then due to virtual short, I can write VD equal to VA. So this is nothing but VA, and again if this is VE, then VE equal to VB. So this is nothing but VB. And now since we know these two potential, we can write VAB by R2 is the current I2, right? and then we can again write VCF is nothing but I2 times R1 plus R2 plus R3 by the simple law of network theory. And we already know that I2 is VAB by R2 times R1 plus R2 plus R3. Now VAB is given, R1, R2, R3 values are given, so it is easy to calculate VCF, which can be calculated as 2 millivolt divided by R2 is given in the problem as 2 kilo ohm, and R1 is 9 plus R2 is 2 and R3 is 9, all in kilo, so they can cancel, and we ultimately have 20 millivolts as the value of VCF. So I think the first part was easy, and now let us go ahead with the second part. So second part, what it is asked is to calculate V0, is the output voltage of this instrumentation amplifier. So again I want to just show you this network. And find the value of V out. So we know VCF is 20 millivolts, and we need the value of V0. Now this stage, if you see, this stage 2 gain we need to determine. If we know the gain of stage 2, which is nothing but G2 if we assume, then we can write V0 equal to G2 times VCF, because this VCF is the input to the second stage. Output is V, which is nothing but this current times this RL, which is nothing but V0, right? So V0 is the output voltage. Now what should be the gain of this stage? If I assume this differential voltage to be VCF, and due to the symmetry of R4, R5 and R6, R7, I can just go ahead with this part assumed to be 0 and this part to be VCF. So you know this is a negative feedback based circuit, and the gain should be R5 by R4. So G2 is R5 by R4. If you are not able to see, you can just draw this simple circuit where you can consider this node as VCF, and this node you can assume as 0, and then this node as R4 and R5 connected to the output as V0. Now you know this one is 0, so VCF minus 0 by R4 should be equal to, since no currents can enter here, so the current will go like this, and this current will be nothing but 0 minus V0 by R5. Okay, so we have V0 by VCF equal to R5 by R4. So this is nothing but the gain of this stage. So gain of this stage is already determined, which is R5 by R4. So now once you have R5 by R4 as the gain, we can find out V0 as VCF times the gain, which is nothing but 20 times gain is R5 by R4, which is nothing but 12 by 6 millivolts, because kilo and kilo can cancel, so 40 millivolts. V0 is nothing but 40 millivolts. Now they have asked in part C the total gain. So we know already you determined the first stage gain, that is from V diff to VCF, then this is stage 1, and
the next gain is of stage 2, which is VCF to V0. Now this stage 2 gain you already know is R4 by R5, which is nothing but 2, and stage 1 gain G1 is what? VCF by VDIF, which is nothing but 20 by 2. So this is 10. So what is G net? It is nothing but G1, G2, which is nothing but 2 into 10, which is 20. So 20 is the overall gain of this instrumentation amplifier. And coming with the final part, the internal input impedance. You see from this side, since no currents can go through these ports, what we can infer, the internal impedance is infinite. So this is because input current is 0. So infinite, right? Infinite input impedance. So these are the 4 parts how you solve this problem. So just see the next problem where you have a different network configuration comprising of 2 back-to-back connected operational amplifiers, and you have been asked to find out the waveform and comment about their peak-to-peak values and the slopes and the frequencies and all those parameters. So kindly analyze this network. I'll give you some time and you can just solve yourself faster. So try this problem. So I request all of you to try this problem, okay? So I request all of you to try this problem, okay?
So I request all of you to try this problem, okay? So I hope all of you have tried this problem. So let us come to the solution. So for part 1, you see that a waveform of V1 is being asked and 4 options are given: triangular, square, pulse train and sinusoidal. Where you see all the 4 options are comprising of not a steady value but a toggling value. So in order for V1 to be toggling, these two voltages should not be equal. There should be some differential voltage that should be impressed across the op-amp such that it is driven as per the history from that state to the next saturation state. That is, for example, if this input was higher than the threshold, or which is 0 volts of this negative node, then the output will be driven to the plus Vsat. And if it is lower than 0 volts, then it will be output will be driven to minus Vsat or VCC, whatever you say. So now we know that this V1 is toggling. So virtual short doesn't hold. So now we need to determine that condition. And first we have been asked to determine the waveform of V1. So what can you conclude about the waveform of V1? Any idea? I told you that it is in toggling state, right? As per the input to this node, because this is node is the negative node is already grounded. So if you want to determine this voltage Vx,
what can you say? V2 minus Vx by R2. This current should be equal to this current, which is nothing but Vx minus V1 by R3. And hence we can get what? V2 by R2 minus Vx by R2 equal to V1 by R3 with a minus sign plus Vx by R3. And hence we can write V2 by R2 plus V1 by R3 is nothing but Vx 1 plus R2 by 1 plus R3. And if we multiply R2 R3, then what we will get is R3 V2 plus R2 V1 divided by R2 plus R3 is nothing but Vx. So R3 is 3, so 3 V2 by R2 plus R3, which is 5, plus, because kilo and kilo will cancel, right? And R2 is 2 divided by 5 is equal to Vx. So now what can you conclude about the toggling condition? That whenever Vx will be greater than 0, then Vout will be driven from minus Vcc to plus Vcc. And whenever Vx is less than 0, V0 will be from plus Vcc to minus Vcc. So this is toggling condition, and this waveform of Vout will resemble a square wave, just like a pulse, square pulse going from positive half cycle to negative half cycle. So it will be option B. So now coming to the next part, the waveform of V2 is being asked. So if we know the waveform of V0 actually, or V1, sorry, the output voltage, then this waveform is square. So this waveform is also square, which is coming as input to this stage. And what is this stage? Can anyone comment about this stage? If this is the input, so this is basically an integrator circuit where you see a resistance and a capacitance connected to the negative port, that is the inverting port of the op-amp. So this is an integrator circuit. So if you know the incoming input signal is a square wave, so you can obviously comment that the output of this stage, which is nothing but an integrator in between, will be a triangular wave. So option A, sorry, is correct, which is triangular wave. So V2 should be triangular wave. Now coming to the next, you have these 5 questions about the peak to peak value of V1, the peak to peak value of V2, the slope of the triangular waveform, which is nothing but of V2, and the frequency and the resistance, and its correlation with the waveforms, the time period and the peaks, all those things. So let me increase my number of slides, and then I can bring this here. So Next part asks about the peak to peak value of V1. So V1 is a square wave toggling from plus VCC to minus VCC, again back to plus VCC. And now what is the value of plus VCC minus VCC? This is nothing but plus 15 volts to minus 15 volts. So V1 peak to peak, what we can write is 15 minus minus of 15, which is nothing but 30 volts. And what can you comment about V2 peak to peak? Kindly think. V1 peak to peak was easy because it was a square wave toggling from plus VCC to minus VCC. And now we are being asked to, so this is done. But now we are being asked to calculate the peak to peak value of this voltage, which is V2. So kindly think about this. I will give you 1 to 2 minutes and then we'll discuss. So I think I have given you enough time to think about it. So kindly see one thing. You already know that V1 is toggling, right? So V1 is toggling. Another thing you know, and you can see also that this is a positive feedback which is fed to the non-inverting end of the wave. And V1 is toggling. So this circuit is basically resembling a Smith trigger arrangement. Right? So now can you write down the toggling condition, because we have already determined what is the value of Vx. We have already determined that, right? Vx is 2 by 5 V1 plus 3 by 5 V2. So if we know that if this is greater than 0, which is nothing but this node, then we have the toggling from minus VCC to plus VCC of V1. And we have the reverse, that is lower than that negative inverting node. Then the reverse from plus VCC to minus VCC, V1. So for each of these we already know what is the value of V1. That is initial value of V1. Kindly be careful. So case 1 and this case 2. So let us calculate for case 1. So what we can write? 2 by 5 times. So it is about to be positive, that is greater than 0, just greater than 0. Before that, what was V1? V1 was negative, right? You plug that here, which is nothing but minus 15 plus 3 by 5 into V2. V2 we want to determine, right? So from this condition, what can we write is V2 should be greater than 10. So this is 1. And then let us calculate for case 2. 2 by 5 times V1, but V1 initial was plus BC, plus 3 by 5 of V2. V2 we want to calculate for this case, which is nothing but we are getting minus 10. So if V2 is less than minus 10, which is the LTP, then it will drive the output to the negative saturation point, and it is UTP because it's the input V2. Sorry, if V2 is greater than 10, is not input but this signal, then it will drive it to the positive point. So now we know these two things, then we can calculate the peak to peak value of V2, because as soon as this is violated, then again the output will be fed back and accordingly V2 will be changed. So V2 peak to peak, what can you tell, is 20 volts. That is nothing but UTP minus LTP. I think this is easy, right? So let us see what is the next problem. How much is the slope of the triangular wave? So slope is being asked. Slope of triangular wave is being asked. Means that this waveform Vx or V2 so how can you determine the slope is the question. Any idea? So slope can be determined from current, because what is current? This current. Yeah. Just check it. Type it. So this current is flowing from this capacitor like this, because it cannot go here, neither here. Two points are isolated, right? So the current is flowing like this, and due to the negative feedback arrangement of the first stage, we can assume virtual short, which is nothing but this point is also at 0 volts. And let us consider the rising edge where V1 is positive. So V1 positive means it is plus VCC. what you can write is plus VCC divided by minus 0, obviously the voltage difference, divided by 20K is nothing but 0. So when V1, so we can write what? The capacitor current is C dV dt. This is the current, right? So this is the slope of the triangular wave being integrated, that is V2. So now what I need is, we know E is your VCC by 20K, which is the current, is C dVc dt, and we need this. So what is this? C dVc dt. From that we can write dVc dt is 15 divided by 20 into 10 to the power 3 multiplied by capacitor. Capacitor value is 250 microfarads. So what it is coming? It is in volt per second, I can write. So if we calculate, so I'm getting 3 volt per second. So we have done these parts. Now the frequency of V1 and V2 are being asked. So kindly try the frequency of V1 and V2. Kindly try this. So the reason I'm giving you some time and letting you solve the problem is because otherwise it will not be helpful if I just throw the solution upon you. You should first apply your own mind and try the numericals, and then I can discuss with you and solve or give you some idea how to solve the problem. So that is the whole philosophy. These sessions are meant to be interactive, and hence we are giving you the time for doing it yourself and just checking your concepts, and then tally with the simulation being provided. So this is V1 and this is V2. Like this, which is from plus 10 to minus 10. So we are estimating this time period in one cycle and this time period in another cycle, calculate the net time period. Okay, so kindly try now, because this V2 is the voltage impressed across the capacitor. So this is half of the cycle, I can write T1, and this is half of the cycle, I can write T2. So as you can see, we need to fix the limits, right? So it was from plus VCC to minus VCC, right? Plus VCC to minus. Then again minus VCC to plus VCC, right? Just see the waveform. So I can write it as summing T net, I can write equal to T1 plus T2, or we can write what? 2 times C times VCC minus of minus VCC. Because time cannot be negative, right? So C minus minus of VCC divided by what I can write is this current. So this is V1. So this is VC, which is the capacitor voltage, and VCC means plus V set, which is nothing but V1 upper maximum value divided by 20K. This is the current, right? We are just following I equal to C dV/dt. So this is the current, and VC is the voltage impressed across capacitor. VCC is the upper limit of V1. So these two are defined. Now calculate what it is coming. So C is 250 microfarad, and it's 2 times, so VC is nothing but plus 10, minus VC is minus 10, so it is 20 times 2. So 2 times C times 20 divided by plus 15 divided by 20. So that will be the answer, which is nothing but, so T is coming as 40 times 250 microfarad in multiplied by 20,000 divided by, so it is coming 13.33 seconds. So the frequency now I can find from here is 1 by T, which is nothing but 0.075 hertz. The frequency you found that as 0.075 hertz. So obviously you note that without the participation of the capacitor, we could not have determined the frequency. So both these two values R1 and C, so I will write R1 and C govern the frequency of V1 and V2, along with, yes, R1 and is obviously along with the voltage levels, but I have talking about the elements, right? Which are the elements which are governing the frequency, because it is asked in the question. Which resistance in the circuit can be changed to change the frequency without changing the peak to peak value of any of the generated waveform? So peak to peak value, if you see, all the peak to peak values, they are not dependent on any resistance values, right? V2 peak to peak is dependent on resistance value, right? V1 peak to peak is not dependent. So I will write V1 peak to peak is independent of any elements, but V2 peak to peak is dependent only on stage 2 register values of Smith trigger arrangement. So these two you understand, but the frequency of signal wave V1 and V2 only depend on stage 1 R and C. That means stage 1 R is nothing but R1 and this is C. This is R1 and C. Only these two. So this is the final part of the problem, which is G. So if we have solved, then this is G. So this is the solution. Correct? I hope with this you have got an idea of how to deal with such problems. So now coming to the use of this measuring instrument with the operational amplifier, so which we call as the instrumentation amplifier based arrangements. So now see, this circuit is a easy problem, the first problem based on this kind of metering arrangement with the operational amplifier. So the problem is on your screen, and I request you to kindly attend the problem. So we should not spend much time on this problem. This is given that the PMMC voltage is 2.9 volts. This is already given in the problem. Now they are asking you to estimate the input current, which is this one. So no, this part will not receive any current because this is directly, sorry, not this part, because this part is interfaced to the other part of the circuit. So the input of the op-amp will not receive any current because the input impedance is infinite. So this part will not receive any current. So this current will just go like this, right? And this current will also be zero, and this current will be in loop like this. So what you can, you have to estimate two parts: the input current and the when the meter reading is 2.9 volt, and the input resistance of the electronic ammeter based arrangement. So you can see that this point is at zero potential. So I in into 1, this is the voltage being applied. So this is nothing but You can assume virtual short, and now you can write this as Vp, this as Vn. So I can write that since this is grounded, what is the input voltage is I in times 1. So this voltage is Vn, right? So I know this voltage difference is I in, and if I can know Vn, then Vp is Vn. So I need Vn because I in is nothing but Vp, because this potential is Vp, right? So Vp minus 0 volt is nothing but I in, 1 into I in. So now what I can write, I need Vp, and Vp is nothing but Vn. So Vn can be calculated. So how to calculate? So what is voltmeter is measuring? This voltmeter is measuring this voltage difference. So if I know this is 2.9, so what I can write? 2.9 divided by 98 plus 2 kilo is the current, which is nothing but 0.029 milliamps. So now this is the current. So this multiplied by, so current will be like this, right? So this, so current multiplied by 2 kilo is the Vn, which is nothing but Vp. So Vp is nothing but 0.029 times 2k, and this is milli. So milli and kilo will cancel, and this will be 0.058 volts. So this is nothing but In. So In is from this relation. So this is 0.058. So I can write 58 milliamps. I hope you understand what is going on. It is just application of virtual short and determination of Vn, from which you know Vp because they are all same, and this is nothing but In times 1. So voltage equalization will give us this relation, and from this virtual short we equate the two and get this one. We find the current through the meter reading, and then from that we determine Vn, and from Vn we can determine obviously In, and the current we can write just by applying the Ohm's law. So this is the very easy problem, and now the next problem is on your screen, and I hope you will solve the problem. So I give you some time. So kindly solve this problem.
Sorry, the problem is on your screen now. So I give you 2 minutes to solve it. So the question was easy. One thing only you need to know that what the PMMC meter measures. So PMMC meter always measures average. So irrespective of whatever is written, you need to know and use this information. It is very important in this kind of arrangements. So either you have ammeter or voltmeter, but the PMMC based meter will always measure the average value of the incoming signal or the signal flowing through it. So you have a arrangement where you see that if you have a current entering through this, then the current in the positive half cycle will pass through the meter and will go like this, right? Obviously, if you have some grounding arrangements, it will pass on. And I may use another color. And during the negative half cycle, it will again return. So what will the path is? It will return through this path. So you see this current is flowing through this resistance. 2 milliampere current is flowing through this resistance, and this resistance is 2 milliampere times 25 kilo, which is the voltage. But what is this voltage? PMMC is not reading this voltage. PMMC is reading the average voltage. So Vmax
by pi. This is the voltage that the PMMC is reading. Sorry, this will be the average voltage. And this average voltage will be same as 2 Vmax by pi, which is the voltage impressed across the PMMC. So whatever the PMMC will read and will result the current, that will be also including the diode drops, right? So I need VRMS, which is nothing but Vmax by root 2, and from here Vmax can be written as 2 milli times 25 kilo times pi by 2 divided by root 2. So this is VRMS, which is nothing but 55.53. But this voltage was actually the average voltage of this side, but the drop will also happen. So you can consider the 0.7 plus 0.7 drop. So these two drops are always present in the forward cycle and the return cycle, that is the positive and negative cycle. So this will also contribute to the main average value of this signal. We added hence. So you can consider this plus 1.4, and it will come somewhere around 56 volts. So this is the RMS value of the input voltage corresponding to full scale deflection. So for 50% deflection, what will happen? How much voltage? It is a linear scale. So half of that, half of 56, we are going to get 28 volts. I average it will, because average value, we have the average value, average input and average voltage and current both. So now the resistance can be calculated as V average by I average. I average is 2 milliamps and V average can be calculated as 50, because 2 times 25, so 50k. But this is k times milli, because what is it? V average is 2 milli times 25 kilo, so it is 50. So that 50 we plugged here and divided by 2 milliamps, it is 25,000 ohms. So 25,000 ohm is the input resistance. So kindly see the next problem.
So now you know you have a half bridge arrangement, and this voltage is same as this voltage, and what you need, VMMC meter reading is 0.5 volts, so this you know 0.5 volts, and this you need this voltage. So 0.5 divided by 7 plus 1 is the current times 1 is 0.5, because kilo and kilo will get cancelled. So 0.5 by 8 is the voltage here or the voltage here. But what is this voltage? This is the half wave rectified form. So 2V, not 2, the half or half wave, you have Vm by pi. So if this is V in, this is V in, and this is V in. So 0.5 is Vm by pi. So what is V? 0.5 by 8 into 1. It's nothing but the average value of this node. This is average value of input, right? So what is input? V max by pi. This is the average value of input. If we equate, so this is the average value of voltage, and this average value of voltage is coming here. And the PMMC is measuring the total, but we want only this much. So 0.5 by 7 plus 1k by into 1. This is the thing. But PMMC is measuring the total. We need only this much. So we use the division rule and calculated how much is this voltage. And this average value is the average value of the input. The average value of the input is this also, Vm by pi for a half wave arrangement. So now you can calculate Vm as 0.5 by 8 into pi. And VRMS is 0.5 into pi by 8 root 2. So VRMS is coming out as 0.138 volts. So kindly solve this problem.
So they are asking you to calculate the input current, right? Sorry, input voltage, maximum and RMS value. So PMMC meter reading is 16 milliamps, which is nothing but the average value of input current. And this is 0 volt. So Im by pi, and this is the average value. So Im can be written as 16 milli into pi, and V in max is nothing but 16 milli amps into pi into 5. So V in RMS is 5 pi into 16 by root 2 into 10 to the power minus 3. So it is coming around 5 pi into 16 divided by 1000 divided by root 2.178 volts. So RMS value is done. Now the maximum input voltage before op-amp can drive to saturation. So that is when this exceeds 0 volts. So at saturation this is 15 volts. That is the average value, and 15 plus 15 minus 0.7, if the voltage comes here, then after drop it will come as 15 only. So if the voltage is 15 minus 0.7 on this side, then we have the saturation. So 15 minus 0.7 by 450 ohm is the current for saturation. Now this current is flowing through the PMMC, which is nothing but the average current. So this is nothing but Imax by pi. So what is the value of Imax? It is nothing but pi. So Imax times R is Vmax, but by root 2 is Vrms. So this value of, because if this side we get 15, then only we will have the saturation. So 15 and this will have drop of forward drop of 0.7. So this side it should be 15 minus 0.7 in the average sense, and we calculate average current, and same current will flow through this also, and we equate with the average current form, and then we find the original current form, and then with the voltage multiplying with the resistance we get the voltage and the RMS voltage. So the answer is coming out as 0.354. Okay, so with this we complete all the variants of the problem, and I hope this session is useful for you. So with this we end the session, and I hope you will be able to solve the remaining of the problems. So thank you.